Okay, I want you to imagine something for a moment. You're looking at a blueprint for a machine.
A really complex one.
Yeah, something that can calculate missile trajectories or, I don't know, forecast the weather, manage a whole global network.
And this machine, it needs tens of thousands of parts. Transistors, resistors, capacitors.
And here's the kicker. Every single one of those parts needs to be physically connected to the others.
Right. And we're not talking about some seamless high-tech bond. This was a literal physical wire, usually a hand-soldered joint.
So for, say, 30,000 components, you're looking at what? 50,000 individual connections?
Or more. And every single one of those connections is a place where the whole thing can fail.
A potential point of failure.
It's worse than potential. It's a statistical certainty. If you have 50,000 joints, and each one has a 99.999% chance of being perfect.
Which is incredibly optimistic.
Wildly optimistic for a manual job. Even then, the probability of the entire system working correctly drops to basically zero. You build it, test it, it fails. You find the one bad joint, fix it. Another one fails somewhere else.
It was a statistical death sentence?
For anything really complex, yes.
Yeah.
It was the ultimate bottleneck holding back the digital age.
So that is our mission for this deep dive. We are going to unpack the radical solution that let us escape that exact trap. We're exploring how we went from soldering these just mountains of separate pieces into a mess to effectively printing an entire world of computation onto a tiny piece of silicon.
And that little piece, the chip, actually gets its name from that idea. A chip is a splinter, a fragment broken off from a single whole piece.
Because the breakthrough was treating the entire circuit as one continuous, indivisible thing.
Exactly.
Okay, so let's start there. Let's go back to the old world, before the integrated circuit. What did electronics actually look like?
Well, they looked like huge cabinets full of stuff. They were massive, power-hungry things.
Like the old UNIVAC or ENIAC computers.
Exactly. Those used vacuum tubes. But even when smaller transistors came along, the basic method didn't really change. It was all built like a giant constructor set.
So you had all these discrete parts.
Right. The transistors, the resistors, they were all these little physical details. You know, little boxes and barrels that you had to physically mount on a board and wire up.
Which means, as the designs got smarter and more complicated,
The real work, the real struggle, wasn't inventing the circuit anymore. It was just the sheer brutal effort of trying to assemble it without it failing.
the ingenuity went into just managing the chaos.
That's a perfect way to put it. You could have the most brilliant design on paper, but if it needed 1,000 transistors, it needed thousands of manual connections.
And even with printed circuit boards, the PCBs.
So PCBs helped. They give you neat copper lines instead of a rat's nest of wires. But the core problem, it was still there.
Which?
You still had to manually insert and solder every single component onto that board, one by one. The problem wasn't the layout on the board. It was the insane number of physical contact points that needed a human to make them.
Which brings us to this idea they called the tyranny of numbers. This was the crisis, right?
It was the crisis.
Yeah.
Because the individual parts, the transistors, they were getting better, smaller, faster, much better than vacuum tubes. But progress was just grinding to a halt.
Why? If the parts are better, why doesn't the machine get better?
Because the system's reliability wasn't about the quality of the parts. It was about the chaos of the connections between them. That phrase, the tyranny of numbers, really took hold in the late 50s. Engineers just realized they had hit a wall, a statistical wall they couldn't climb.
Can you give us an example? What did that wall look like in practice?
Think about early defense systems, guidance computers. They needed to be ultra-reliable,
Of course.
but they needed tens of thousands of components. The math showed that to get even one of those systems working reliably, the failure rate for assembly had to be so low it was physically impossible with human labor.
So the failures weren't even electrical, they were mechanical.
Almost always. A bad solder joint that broke, a wire that expanded with heat, a tiny bit of dust on a contact point. It was the physical connections.
So better training for the assemblers wasn't going to cut it.
Not even close. You needed a radical solution. The whole way of thinking had to pivot. They had to stop asking, how do we make the connections better?
And start asking.
How do we get rid of the connections entirely?
And this is where it gets really brilliant, because the answer wasn't about assembly at all. The question changed from, how do we build this better, to, what if we don't build it at all?
That was the pivotal insight. That was the leap.
It's like switching from, I don't know, hand painting every letter in every single book.
To creating a printing press. A template where the whole page appears at once, perfectly formed.
So what was the technical version of that leap? What did they realize about the transistor?
They realized that a transistor, fundamentally, isn't a detail you place on top of a material. It's a structure you create inside the semiconductor material itself, inside the silicon.
You're not adding bricks to a foundation, you're carving the rooms directly into the foundation itself.
A perfect analogy. You stop building and you start printing. You print an entire city of electronics all at once using light and chemistry. And suddenly, all those failure-prone connections, they're just gone.
Okay, so let's walk through that magic. How do you print a city inside a crystal? What's the actual process?
Well, the key thing to remember is that the transistors aren't squeezed in or installed. They're literally grown, layer by layer, directly inside the silicon.
And it all starts with the foundation, the silicon itself.
It starts with a wafer, a perfectly clean, perfectly flat, flawless slice of crystalline silicon. That's your ground floor.
And what goes on top of it?
First, an insulating layer, usually silicon dioxide. Then on top of that, a light-sensitive chemical called a photoresist. Think of that as the photographic film that's going to capture the blueprint.
And then comes the key step, I assume, transferring the blueprint.
Exactly. Photolithography. This is where it all happens. You take a mask, which is like an incredibly detailed stencil of your circuit, and you shine ultraviolet light through it onto the wafer.
So you're literally printing the circuit's pattern with light.
You are. And the precision today is just, it's measured in nanometers. It's staggering. Where the light hits the photoresist, the chemical changes.
Like developing a photograph.
Just like that.
Yeah.
And that change lets you wash away either the exposed or unexposed parts, creating these tiny microscopic windows in the layers below.
Okay, so you've opened these little windows down to the bare silicon, right where you want your components to be.
Precisely. And now through those windows, you perform the next critical step, which is called doping.
Doping? What's that?
It's where you intentionally introduce specific impurities, tiny amounts of other elements like boron or phosphorus, into the pure silicon crystal.
Why do that?
Because pure silicon is just a semiconductor. By doping it, you create distinct regions p-type for positive and n-type for negative. These chemically altered zones with different electrical properties are the body of the transistor.
So you're not building a transistor, you are chemically transforming a tiny part of the silicon into a transistor.
You've got it. It's now an integrated part of the crystal itself. Not placed on it, but created within it.
And then you just repeat that process layer by layer to build up the complexity.
Exactly. And for the final step, to connect all these millions of tiny structures, you deposit a thin layer of metal, like copper or aluminum.
And you pattern that with photolithography too?
You pattern that layer of metal to create all the wiring. It's called metallization. And those tiny metal traces replace every single one of those thousands of hand-soldered wires. Everything is now inside the chip. The assembly problem is solved.
It's an incredible story. And like a lot of these huge inventions, there are two names that always come up. Jack Kilby and Robert Noyce.
Right. The two fathers of the integrated circuit.
How are their contributions different?
You can think of it as principle versus production.
Yeah.
Jack Kilby at Texas Instruments was the first guy to prove the principle.
He made the first one.
He did. It was the summer of 1958. Most of the company was on vacation, and he was a new hire, so he didn't get vacation time. He was alone in the lab and just had this idea.
So he was kind of breaking the rules while everyone was away.
Totally. His first working model was ugly. It was this rough-looking piece of germanium with wires sort of glued to it, but it worked. It was the proof of concept, the aha
moment. And Robert Noyce at Fairchild Semiconductor.
Noyce is the reason we have this technology in our pockets today. He invented the planar process. Kilby proved it was possible. Noyce figured out how to make it scalable and manufacturable. His approach allowed everything, the transistors, the insulation, and crucially the metal interconnections, to be created as one unified process, all on the flat top surface of the wafer. That method is the foundation for mass production. It let us make millions and now billions of them.
So Kilby had the idea, Noyce created the factory.
That's a great way to summarize it.
Which, of course, brings up the Nobel Prize question. In 2000, Jack Kilby was awarded the Nobel Prize in physics for it. Alone. Why wasn't Noyce recognized with him?
It's a sad but simple reason. The Nobel Prize cannot be awarded posthumously. Robert Noyce had passed away by the time the award was given in 2000. It was purely a procedural rule from the Nobel Foundation. It takes nothing away from his monumental contribution. His process is in every device we use.
That puts a fine point on it. Okay, so let's wrap this up with the big picture. For you, the listener, what really changed? When that bottleneck of manual assembly just vanished, what were the big effects?
There were three, and they changed everything. First, and most important at the time, was higher reliability.
Right.
By getting rid of thousands of mechanical solder joints and replacing them with chemically bonded structures inside a crystal, the chance of failure just plummeted. You took the human error of the soldering iron completely out of the equation.
Computers went from failing every few hours to running for years.
And that's the difference between a lab experiment and a product you can sell. The second was speed.
Higher speed.
Because everything is so tiny and so close together on a chip, the electrical signals have almost no distance to travel. That cut down signal delay and boosted calculation speeds exponentially.
And the third effect, the one that really drives our world today, scaling.
Scaling. This is the magic of it all. Because it's a printing process, you can always work on making the printing finer, more detailed.
Making the letters smaller.
Exactly. So engineers could pack exponentially more transistors into the same small area. This is what became known as Moore's Law.
Gordon Moore's observation that the number of transistors you can fit on a chip doubles about every 2 years.
And that law has held up for decades, all thanks to refining Noyce's planar process, using light and chemistry to print ever finer features.
To the point where today, a chip on your finger can hold billions of transistors.
More transistors than the number of people who have ever lived on Earth. It's a density that was it was pure science fiction 50 years ago.
So we went from the tyranny of numbers, where more complexity meant certain failure, to a world where complexity is just managed by printing with light.
The microchip gave us the brain, the raw computational power.
But a brain isn't enough for a fully digital world. You need eyes to see the world, and you need nerves to send the data.
And that brings us to the next great revolution, which, funny enough, was also all about light and material science. It's the other half of the story.
We have to explore how a CCD matrix, the sensor in a digital camera, turns light into an electrical charge and then into the language of numbers.
And then how optical fiber, which is basically hyper-pure glass, carries those numbers across oceans with almost no loss.
Light becomes data, and data is sent as light.
The whole modern world rests on those two intertwined ideas. It's fascinating that the 2009 Nobel Prize in Physics actually recognized both of them together, the CCD sensor and fiber optics.
They completed the loop.
The loop that the integrated circuit started.
So a final thought for you to ponder until our next deep dive. Who taught light how to speak the language of numbers, and how did we convince glass to carry those conversations across the entire globe? We'll find out next time.